heat and work. We've defined that energy is constant and energy is equal to the amount of heat plus work. We've looked at how to figure out whether heat is positive or negative, what's happening to the system, what's being transferred, etc. Now we're going to take a little bit of a deeper look at heat separately and then work separately. We know heat is a transfer of thermal energy. And thermal energy always flows from matter at higher temperatures to matter at lower temperatures. Perfect example of that is a hot cup of coffee transfers thermal energy as the form of heat to lower temperature surroundings as it cools down. So when you make a cup of coffee and you place it on your table and you just walk away for a little while, that cup of coffee transfers energy as heat, thermal energy is a form of heat, to lower temperature surroundings, where the surroundings are the table, the air around it. Since it's not sealed, that's why it cools down. The thermal energy in the molecules that compose the hot coffee distributes itself to the molecules in the surroundings. The heat transfer from the coffee to the surroundings stops when the two reach the same temperature, thermal equilibrium. So at first, the hot coffee is hotter than the surroundings, and it sits there, and the molecules and contents that make up the hot coffee distribute itself to the molecules in the surroundings. And eventually, all of these molecules reach the same temperature, where at first, the hot coffee has a hotter temperature and the surroundings have a cooler temperature. Eventually, they reach the same temperature. That's when you have something called thermal equilibrium. At thermal equilibrium, there is no additional net transfer of heat. So now the same temperature is reached, and there's no more transfer of heat. So when a system absorbs heat, its temperature always changes. Heat is absorbed by a system, and its corresponding temperature change is completely and directly proportional. So Q is proportional to the change in temperature. And this constant proportionality is the system's heat capacity, a measure of the system's ability to absorb thermal energy without undergoing a large change in temperature. So a way to see how much heat is needed without undergoing a very, very significant temperature change, without having to change the temperature by a lot. The quantity of heat required to change its temperature by 1 degree Celsius. So we say that the heat capacity is the quantity of heat required to change its temperature by 1 degree Celsius. So really small change in temperature. So just the heat of any substance needed for 1 degree Celsius of temperature change. So that's why it's really good to use as a constant, because it's all these heats that's been found for different things by just 1 degree Celsius temperature change. When you place a steel saucepan, for example, on a kitchen flame, its temperature rises really, really fast, right? When you're just placing the steel saucepan on a kitchen flame, it goes up. Now, if you add water, though, the temperature doesn't rise as fast. It rises a little bit more slowly. Just like if you add a cup and you put a flame underneath, it's going to heat up really, really fast. But if you add water in that beaker, that cup, it warms up a little bit more slowly. What happens is when you add the water, the same amount of heat must now warm more matter, right? Because at first you just have the saucepan, so there's less matter, and therefore the heat can be transferred a lot more quickly. But if you have more matter because you added water, you added more particles, it therefore is going to the temperature and the heat is going to rise a little bit more slowly. Heat capacity is an extensive property, therefore. This is kind of an explanation. So because we're talking about how if you have less matter, the temperature is going to rise a lot faster. If you're adding more, it's going to rise a lot slower. So that amount of heat needed to raise by 1 temperature is dependent on how much you have. So heat capacity is an extensive property. It depends on the amount of matter being heated. That's kind of one reason why when you're adding more matter, the temperature rises more slowly. Also, water is more resistant to temperature change than steel. Water is intrinsically higher and has an intrinsically higher capacity to absorb heat without undergoing a large temperature change. That means that water can absorb a lot more heat without needing a big change in temperature, whereas steel, for example, needs a lot more of a temperature change to absorb heat. Because of this intrinsic behavior of water, because it doesn't need a significant temperature increase to actually absorb heat, the measure of this capacity to absorb heat is its specific capacity. The amount of heat required to raise the temperature of 1 gram by 1 degree Celsius. So note that just heat capacity was the amount of heat needed to change by 1 degree Celsius. Where heat, we look at joule, and temperature, we look at degrees Celsius. Now with specific heat, we added that term specific heat in front of it to kind of account for the extensive and intrinsic properties. Specifically the intrinsic, because of water being more resistant than the steel for the temperature change. Now the specific heat of capacity of any substance is the amount of heat required to raise the temperature of 1 gram by 1 degree Celsius. So now the unit is joules over grams times degrees Celsius rather than just joules over degrees Celsius. Another form of heat capacity is sometimes it's reported in molar heat capacity. The amount of heat required to raise a temperature of 1 mole by 1 degree Celsius. Joule over mole times degrees Celsius. It's always the heat over a temperature change by 1 degree Celsius, or when you're talking specific heat, it's a gram. So for example, iron, copper, gold, they all have very specific heat capacities for 1 gram of the substance of a 1 degree Celsius change. Now, all of this can be added together to kind of define different aspects in a chemical reaction. The specific heat of a substance can be used to quantify the relationship between the amount of heat added to a given amount of the substance and corresponding temperature increase. Woo, that was a lot. Basically, this means that specific heat, right? When we're looking at specific heat, we have joules over gram degrees Celsius. So I can figure out heat, Q, I can figure out mass, and I can figure out temperature. And since it's a reaction, we're always thinking temperature change. Now this brings us up to this heat equation that you're looking at here, where mass, which is in grams, is equal to specific heat capacity, which is joules over gram degrees Celsius, times change in temperature, which is degrees Celsius, and that gives you the unit for Q as in joules, which we already know. And you can use this to find anything. What if you're given a certain amount of heat and you're given mass and you're given heat capacity and you're trying to find the final temperature you would need? Or you have all the other ones and you're trying to find heat, or you don't know the specific heat of a substance. You're trying to find an unknown, for example, and you can find the heat, the mass, the temperature change, and you want to know what substance you have. You can identify through the specific heat capacity because they're specific for different types of substances through different experiments. Let's look at an example. How much heat is required to warm 15 liters of water from 25 degrees Celsius to 100 degrees Celsius? The density of water is 1 gram per milliliter. Well, I'm trying to figure out the amount of heat required. So I'm looking for Q is equal to MCAT, what I like to say. Mass, specific heat, times final temperature, and initial temperature change. I'm given my temperature change. So I have T final is 100 degrees Celsius. T initial is 25 degrees Celsius. I'm given the density, which is 1 gram per milliliter. And I'm given a volume of 15 milliliters. And that's it. And I want heat. So I already know my equation down here. And I need to find mass. And I need specific heat capacity. Well, I'm told that I'm using water. So then I would look this up, or it's given to me. But the specific heat of water is 4.18 joules per gram degree Celsius. So I have that. Now mass. Well, I'm given here density and volume. So I can use the density and the volume to find the mass. I'll first have to convert the liters to milliliters, which gives me 1.50 times 10 to the third milliliters, because I multiply that by 1,000 milliliters. Then if I multiply that by the density, I will get my grams of 1.5 times 10 to the third grams, which then you would just plug back up here, which I'll just do in a different color. So then you take your mass, 1.5 times 10 to the third grams, times the specific heat, 4.18 joules grams Celsius, times the temperature change, final minus initial, degrees Celsius, and Q will then equal 4.70 times 10 to the fifth joules. So, using all the different amounts, the heat or the mass or the temperatures, the capacity, you can find different amounts or different things in a reaction that you're looking for. Making sure, however, that the units are always the units that you want. Looking at another example. Suppose you find a penny 3.10 grams in the snow. How much heat is absorbed? Immediately I know I'm looking for Q equals mc delta T. By a penny as it warms from the temperature of the snow, -8 degrees Celsius, this is my T initial, to the temperature of your body, 37.0 degrees Celsius. I have my mass. Okay, so I'm talking about a penny. So I need to find the specific heat of copper. I would look this up. And it's 0.385 joules grams Celsius. Now I have everything that I need. So I plug in my mass, 3.10 grams, times 0.385 joules over gram degrees Celsius, times the temperature change, which is 37 minus -8 degrees Celsius, which then equals 53.7 joules. So knowing if you're looking for heat, heat is just in joules. So you need to look up the specific heat if it's not given to you or that's not what you're solving for.